Hello and welcome to our lessons on metals and non-metals and their positions on the periodic table. And we're also going to do some work on groups, periods and electron configuration. We're going to be talking about the properties of metals and non-metals. That word in this context means a characteristic that you can use to describe something. So you can maybe use one of these words here to describe a friend. You might say they're cheerful or helpful or quiet, and that would describe their character. When it comes to the properties of metals and non-metals, you're just using words to describe what they're like so you can identify them. Something like shiny or solid. You need to know the names of some properties of metals and non-metals. It's worth recognising that they are opposites, so if one is shiny, the other will be dull. I'm going to quickly go through some of these and just make sure you understand which one it is. So lustrous, which means shiny, is metallic. Dull, which is the opposite, is a non-metal. Sonorous, which means it makes a ringing sound when hit, is metallic, and not sonorous would be a non-metal. High boiling points and high melting points, so they're solids at room temperature, are metallic, with the notable exception of this one on the left here, which is mercury. The opposite, low boiling points and melting points, liquids and gases at room temperature, are non-metals. Now, hard and strong are both metallic properties, but they do mean different things. You need to know the difference between hard and strong. Metals are high density. This means that the particles are closely packed together. And non-metals tend to be low density, which means that the particles are further apart. A good thermal conductor means it passes on the heat energy or the thermal energy well. Metals are good thermal conductors, and non-metals are poor thermal conductors or insulators. Metals are also good electrical conductors, which means they pass on the electrical energy well. And again, non-metals are poor electrical conductors or good electrical insulators. Metals are malleable, which means they can be hammered or pressed into shape without breaking or cracking. The opposite of malleable is brittle. That's a non-metal. They're hard, but they're liable to break if smashed. Ductile is often forgotten about. It means it can be drawn out into a thin wire, and that's a metal. And finally, one that we don't often talk about but you do need to be aware of is that metals, particularly transition metals, are also used as catalysts. So they're used in many different chemical reactions to speed up a reaction without being used up. I've left this slide in not so you can do it, but you really need to be aware the obvious questions they're going to ask in an exam situation is the link between the property of a metal or a non-metal and why it's being used for a specific purpose. So for example, copper. Copper is lustrous, it's a good thermal conductor, it's a good electrical conductor. Why is it going to be used for a frying pan? Well, not because it's lustrous. That doesn't matter. Not because it's a good electrical conductor. That's not the point. The reason it's used as a frying pan is because it's a good thermal conductor. It transfers heat quickly. It's going to cook your food quickly. Now, why is copper, the same material, used as electrical wiring? Well, not because it's a good thermal conductor, but because it's a good electrical conductor. So you've got to be really careful that you link the property with the use that the exam question is talking about. Why is it then that metals are on the left-hand side of the periodic table and non-metals are on the right-hand side? In our last lesson, we discussed John Dalton, John Newlands and Dmitri Mendeleev and how they organised known elements in order of atomic mass. Our modern periodic table, however, is organised in order of atomic number. We also discussed that elements with similar properties are grouped together. A group in the periodic table is a vertical column, as you can see in the diagram. Elements in each column have similar properties. So, for example, group 1, they're all reactive metals. Group 7 are all reactive poisonous non-metals. And group 0 are all inert non-metals. But why do some elements share similar properties? The pictures show the first 3 elements in group 1, lithium, sodium and potassium. As you look at them, what's your hypothesis? What's your ideas about why these 3 elements would have similar properties? What is the same about them? Well, hopefully you would recognise that each of them has just one electron in the outer energy level. So group 1 elements have one electron in the outer energy level. That's what we can see here. What would you predict about the other elements in group 1? So if you look here, no matter how big these elements get, you can see that each of them only have one electron on the outer energy level. And this is what gives group 1 their properties. What about group 2 then? Here's the first 3 elements in group 2, beryllium, magnesium and calcium. What's your hypothesis about what causes the properties of these elements? Why are they in the same group? Well, hopefully you would recognise that all group 2 elements contain 2 electrons in the outer energy level, and this is what gives them their properties. So what could you predict about group 3, group 4, group 5, group 6 and group 7? The group tells us how many electrons there are in the outer energy level of an element. So our core concept so far then is the group, and that's the column going vertically down, tells us the number of electrons in the outer energy level of an element. Group 0 wasn't mentioned earlier, and that's because it doesn't quite follow the same pattern. It's a little bit trickier to understand. For now, just recognise group 0 is called group 0 because the outer energy level is full. Now, this could mean it has 2 electrons or it could have 8 electrons, depending on which element you're talking about. So that's why we ended up with group 0, because it didn't fit with 2. You couldn't call it 8, so we ended up with 0. So we've established why these elements are in group 1. They all have one electron in the outer energy level, and that gives them all similar properties. Now you'll notice I've crossed out hydrogen at the top there. Hydrogen does have one electron in the outer energy level, but it's not a metal, so it doesn't really belong with this group, but sometimes it's put with this group. So for our purposes, we're just going to ignore it. So our next question is then, if they all belong in this group, why do they always appear in this order, going down? First lithium, then sodium, and then potassium. What's your ideas? What's your hypothesis? Let's look in a little detail. So first of all, there's hydrogen. That's row 1. We're going to ignore that for now because it's not really part of the group. So lithium, row 2. Now if you look at the lithium diagram, you'll notice it's got 2 energy levels. Row 3, sodium, if you look at the diagram, has 3 energy levels, 3 circles around the nucleus. Potassium, row 4, guess what? 4 energy levels. Rubidium, row 5, has 5 energy levels. And cesium, row 6, has 6 energy levels. I don't have francium, but that would be row 7. The row, or the period, to use the correct term, as in the periodic table, tells us how many energy levels an atom of an element has. So if you look at the picture there, the diagram of fluorine, it's got 2 energy levels, and so it must be in period 2. So our second core concept then is that the period, or that's the horizontal rows, tells us the number of electron energy levels an element has. So how could I use this information? Well, I've got the 4th period, second group. So I could look at my periodic table. I'm looking for the 4th period, recognising that this is period 1 here, even though there's nothing here. Notice my hydrogen is over here where it belongs. That's period 1. Period 2, 3 and 4, second group, I'm looking at calcium. Okay, I've got the 3rd period and the 3rd group for this one. Again, I'm looking at my periodic table. Now you'll notice here I've got, so let's do the period first. So period 1, period 2, period 3. So I'm along here somewhere. Why am I over here? Well, you ignore this orange bit, the transition metals. So this is column 1, group 1, group 2, and group 3 is over here. So I'm looking at aluminium. Okay, 5th period and group 7. So I'm looking for 1, 2, 3, 4, 5. I'm looking for group 7. 1, 2, miss out the transition metals. 3, 4, 5, 6, 7. That gives me iodine. So it could go the other way then. You could be asked to draw something with some information. So you are asked here to draw oxygen. and you would need to do the correct number of energy levels, and you would need to draw the correct number of electrons in the outer energy level, because that's the information we've been learning about. So oxygen, there's my nucleus, is in period 2. So I draw 2 energy levels, and it is in group 6, and so I would draw 6 electrons on the outer energy level. Well, what about the other energy levels, the ones on the inside? Well, the rule is that the first energy level could have 1 electron, it could have 2 electrons, but now it's full. So any more electrons we need another energy level. This could fit a maximum of 8. Now this energy level is also full, so I have to move on to a third energy level, and the maximum for that one is also 8. The rule is you will not move on to the next energy level until the previous one is full. So if I have 3 energy levels, I would assume that energy level 1 and energy level 2 are already full up. So this is something you need to know, the maximum number of electrons in each energy level. First energy level can fit 2, the second energy level is 8, and the third energy level 8 as well. The last thing I want to talk about in this lesson is electron configurations. Configuration simply means how things are put together or the pattern. If I show you this information here, this is the electron configuration for fluorine. The 2 represents the 2 electrons in the first energy level, and the 7 represents the 7 electrons in the outer energy level. Here's phosphorus, and here's the electron configuration for phosphorus. 2 electrons in the first energy level, 8 electrons in the second energy level, and 5 electrons in the outer energy level. So this bit of information here is telling me quite a lot. It's telling me I have 3 energy levels because there are 3 numbers, and it's telling me it's in group 5 because 5 is the number of electrons on the outer energy level. Electron configurations tell us 3 really important things. First of all, it tells us the group number. The group, that is the vertical columns, is the number of electrons in the outer energy level. This is the outer energy level, and there are 7, so that's group 7. Second, it tells us the period. This is period 3 because there are 3 numbers, and therefore there must be 3 energy levels. And finally, it tells us the total number of electrons. 2 plus 8 plus 7 is 17. So there are 17 electrons. And as we all know, an atom has the same number of protons and electrons. If this has 17 electrons, it must also have 17 protons, and that must mean it has an atomic number of 17. This is chlorine. Okay, so if you could pause the video and have a go at this question for me, please. Okay, so what period is this in? Well, period is the number of electron energy levels. So it has 1, 2, 3, 4. So it's period 4. What group is it in? Well, group is the number of electrons in the outer energy level. So it's group 1. And what element is this? Well, 2 plus 8 is 10, plus another 8 is 18, plus 1 is 19. Atomic number 19 is potassium. So have a go at this question for me, please. Pause the video. Okay, so element Z has the electronic structure 2881. Explain how you can tell that the element is potassium. Well, they allowed a couple of options here. So the answer they were hoping for is that you add up the number of electrons, and this is the atomic number, and you look on the periodic table to get potassium. But look at the allowance. Allow has 19 electrons, and on the periodic table, element number 19 is potassium. So you're making that connection. Look at the do not allow. If you just say, oh, it's got 19 electrons, because you haven't made the connection with the atomic number or the protons, you're not picking up the mark. They also allowed it's in group 1 and period 4. Okay, last one for today, guys. Pause the video and have a go, please. An element has an atomic number of 47. Use the periodic table to write the name of this element. So you're looking at the periodic table, you're looking for atomic number, which is the smaller of the two, 47, and you should have found silver, and you would have got the mark if you simply write the formula Ag. Okay, that's it for today, guys. I'll see you later.